plus 1. Is it clear? So now I have given a step input. Let's say a value of kp, gain of the controller is 1. So it will become very easy to understand. So ys upon your xs, that is equals to kc upon kc plus 1 and divided by tau p upon 1 plus kc and plus 1. Just I am assuming that kc is 1 to make these things mathematics very easy to understand, right? So now I want to understand the steady state value. So can I get from here that your, if xs is equals to 1 upon s, so can I get ys that is equals to 1 upon s into kc upon 1 plus kc, fine, divided by tau p upon 1 plus kc plus 1. So if I'll take Laplace of this particular, so what will happen that yt is equals to what? Kc upon 1 plus kc into 1 minus e to the power minus t into 1 plus kc divided by tau p. Fine. So if t tending to infinity, what will happen? Y infinity. That is equals to what? This will be 0. So this is your kc upon 1 plus kc. So at t tending to infinity, we should get value of kc upon 1 plus kc irrespective. I mean, given that kp is 1, right? I am assuming kp is 1. So the response should be like that. This one is t, this one is your yt, and this value is the final steady state value. Are you getting? That is kc upon 1 plus kc. This one is the final steady state value when I am trying to control a first order process with the unit gain and a time constant, right? Fine. But see, one more thing is that since we have given a unit step input, let's try to understand. Since this was your GC, this one was your P. So if I'll give your XS is equals to 1, right? 1 by S means unit step input was there, right? So let's say T and X. So I have given a unit step input. So I would be interested in knowing that if this one is your X, then we will be knowing that y t tending to infinity, it should be equals to 1, right? The amount of input you are giving, you must be interested in knowing, I mean, I should be getting that much input over there. So what is happening over here? So here at a steady state, this one is your yt, right? y yt is equals to this one, you are getting kc upon 1 plus kc, right? So there is a deviation between this final ultimate value of response and at y tending to infinity, right? At y tending to infinity, and that thus the ultimate value of the response does not matches with the desired change. Means if you are giving here 1 unit of change in input, then you are getting a value of kc upon 1 plus kc, and we can vary the value of kc and we can understand, but that is not equals to 1, right? That is something different. Are you getting it? And that will be less than 1 always. Can you see it? This will be always less than 1 because you are dividing kc upon 1 plus kc. So definitely this will be more than kc. So if you will divide kc upon more than kc, this will be less than 1. So if this one is 1 and this one is less than 1, so you will see there is definitely there is some gap between this ultimate value of response and the input change you have given initially, right? So a parameter has been defined to analyze these things, and that parameter is called as the offset, and the offset is equals to what? That the unit step input that you are giving, or a step input that you are giving in a step input, or you can write magnitude of a step input minus, now this one is your ultimate value of response, so yt tending to infinity, and that is your ultimate value of response. If offset is very high, then deviation from this particular thing will be very high. So this is called as this particular gap, we can call it as the offset. So the thing is that our aims is how much we are changing, giving a step change in input, we should get that much output also. So our aim should be to minimize the offset. So aim is to minimize the offset, right? So now we will learn later on how we can minimize the offset. But right now, just try to understand how can we understand how can we calculate the value of offset, right? So now I have defined the value of offset here, that offset is equals to that is change in step input. So I have given a step input 1, and the ultimate value of response we have got is Kc upon 1 plus Kc. So 1 plus Kc minus Kc divided by 1 plus Kc. So if Kc and Kc will get cancelled out, so this will be 1 plus Kc, right? So the value of your offset, that is equals to 1 upon 1 plus Kc. Now you have got this value of offset. So how can I decrease the value of offset? Here, the aim is how to decrease the value of offset. Fine. And we are having a controller in our control. I can change the parameters of controller and I can do anything, right? So you can see in this particular formula, you'll see there is a parameter involving in the offset, which is controller gain. This is a controller gain. Why? Right? So if I increase Kc, what will happen? Offset will get decreased. So if the plot is like that, let's try to understand. This one is ultimate value of response. Now you will tell me that if this one is your first process, this yellow guy is second one, and this this blue guy is your third one, right? Here offset is this one, here offset is this one, and here offset is this one, right? Since this is your change in input, that is 1, let's say, or m. Right now you just try to understand this one is 1. Fine. So this one is your offset 3, this one is offset 2, this one is your offset 1. So for process 1, offset is very less, for second 2, offset is more, and for third, offset is very high. So what will be the value of, let's say, this one, if I will be talking Kc1, Kc2, and Kc3. So what will be the order of Kc? If offset is less, Kc is more. So here offset is less, so Kc will be more. So can I say Kc1 is greater than Kc2 is greater than Kc3? And this is very important kind of observation. Definitely get, I mean, if you'll see the gate previous year question, you will find these kind of questions are there in the gate. Anyone has any doubt? Darshana, any doubt? Is it clear?
Yes, sir, clear.
Okay. So if it is clear, then try to solve one problem I'm giving you right now. And so let's say this one is a process and this one is your controller GC having KC. This is your GF having value 3, and this one is your load, and again this one is GP, this one is your output, GM is equals to 2, let's say your this one is your xs, right? Xs, and I am giving a magnitude of 2 upon s, right? In input, xs is 2 by s. So calculate the offset if kc is equals to 1. So, and the value of gp, 1 upon 3s plus 1, right? Gf is equals to 3 and gm is equals to 2. So now calculate the value of offset from this particular method. Fast. I'm giving you only 2 minutes to solve this problem. Anyone can solve it. It's very simple, no? So see, this one is your y, sorry, and this one is your x. And I am giving a step input of magnitude 2 unit. That's what the case is 2 by s, right? And this is the transfer function of measuring instrument. This is transfer function of controller. This is transfer function of final control element, that is 3. And this is our process that is being controlled in this particular closed loop system. This is our load. So here GP is given. So what will be the transfer function over here? Ys divided by xs. First m is should be to calculate the transfer function. So that is equal to GP GC GF upon 1 plus GP GC GF GM. Right? So can I write KC into 3 into GP divided by 1 plus KC into 3 into GP into GM. So GP is your first order, that is 1 upon 3s plus 1. KC is 1, so KC is 1. So 3 upon 3s plus 1 upon 1 plus 3 upon 3s plus 1 into 2. Is it clear? So 3s will get cancelled out. The transfer function you will get is 3s plus 7. So this is your transfer function, right? So you have got the value of ys upon xs, that is equals to uh, uh, 3 upon 3s plus 1. 3 divided by 3s plus 7. So the aim should be to make this in the standard form, that is tau kp upon tau s plus 1. So I'll convert this into this form, ys upon xs, that is equals to 3 by 7 divided by 3 by 7 into s plus 1. So this will be your kp for the closed loop response, and this will be your tau for closed loop response tau. So since your xs is equals to 2 divided by s, so your ys should be 2 upon s into 3 by 7 divided by 3 by 7 into s plus 1. So this is your m, that is magnitude of input m. So directly I can write yt, that is equals to 2 into 1 minus e to the power minus t by tau, right? 2 into 3 by 7, right? Into it is 1 minus t by tau. Tau is 3 by 7, so that will be equals to 7 by 3. Is it clear? So can I write yt is equals to 6 divided by 7 into 1 minus e to the power minus 7t by 3. Now, since our magnitude of input is 2, right? Here, m I'll be writing 2y, because here you can see this is your 2 and this is called as the magnitude of step input, right? That is 2. So I am writing it as m, and y t tending to infinity. What will be the value over here? That is your 6 by 7. So can I calculate the value of offset? So offset is equals to, that is m 2 minus 6 by 7. that is equals to 14 minus 6 by 7, that is equals to 8 by 7. So you have got the value of 8 by 7, right? So this kind of question is used to, get used to ask this kind of question. So again, this kind of question is very, very important and you should understand these things. Anyone has any doubt regarding this? How we can calculate the offset? Archana, any doubt? Are you getting it? Because every year gate will ask this kind of question. That's why this kind of question becomes very important, right? Okay. So one more question you can solve on the offset, and I am giving you, this is a question from Kafner book that I told you. This is your 1 plus 1 upon s transfer function of controller, and your this one is your 1. This is your C output. This is your input, and this is R. Fine. And again, I'll make it, that is minus, that is plus, and I'll give R is equals to m by s, where m is equals to 3. Fine. So calculate the offset for this process. Calculate the offset first. Anyone has calculated? I don't think why you are not able to solve this very simplest and easy question. So the thing is that first try to understand the process. You should calculate these things. I am not doing anything. This is your controller, GC. And can anyone tell which kind of controller is this? Where have you seen this kind of controller? If 1 upon 1 plus s, if I am writing, so GC is equals to, can I write KC into 1 plus 1 upon tau is. So here Kc is equals to, if I'll substitute Kc is equals to 1, and if I'll substitute tau I is equals to 1, so I'll get Gs is equals to 1 plus 1 upon s. And since this one is your PI controller, proportional integral controller, if you remember the formula of proportional control, transfer function of proportional controller, and this is your process having transfer function is 1. So if transfer function is 1, let's say GPS is 1. So since 1 upon, can I write tau s plus 1 whole to the power 0. So this is your zeroth order transfer function, zeroth order transfer function. So you should analyze all these things also. It's very important to understand the problem. So whenever we want to calculate the offsets, first we have to calculate the transfer function of closed loop. So transfer function of closed loop C upon R. Can I calculate 1 plus 1 upon S multiplied with 1 upon 1 plus 1 plus 1 upon S multiplied with 1. That's it. So that is 1 plus 1 upon S divided by 1 plus 1 plus 1 upon S. Is it clear? So can I write 1 plus 1 upon S, that is equals to 2 plus 1 upon S. So that is S plus 1 upon 2S plus 1. So here you have seen that we have got the value of C upon R, that is S plus 1 upon 2S plus 1. Right? So now the next thing is that R is equals to M by S, that is 3 by S. So can I write C is equals to 3 divided by S into S plus 1 divided by 2S plus 1. Is it fine? So the value of C is equals to, we have got 3 upon S into S plus 1 divided by 2S plus 1. So now, if I want, this is CS, I want to convert this into C2. So I'll have to take the Laplace of this particular function. So if I want to write 3 upon S into S plus 1 upon 2S plus 1, can I write A by S plus B upon 2S plus 1? So that is equals to 2AS plus A plus B divided by S into 2S plus 1. So that is equals to 2A into S plus A plus B. Fine. So that is 3S plus 3. That is equals to, you have got 2A into S plus A plus B. Fine. So now you can calculate, since the coefficient can be made equal, so 3 is equals to 2A. So you'll get the value of A is equals to 3 by 2, that is 1.5. And since A plus B, that is constant, that is equals to 3. So you have, you'll get value of B is equals to 3 minus 1.5, that is 1.5. So now you have got the value of A and B. So you can write directly A, that is equals to CS, that is equals to A. A is 1.5 divided by S plus B. B is 1.5 divided by 2S plus 1. So now if I want to convert this into CT, so can I write 1.5 plus CT, that is equals to 1.5 into e to the power minus T S plus A. So minus S plus A. So AT, right? So I hope you people remember the formula distance. So S plus A will be equals to minus 1 by 2t, right? 1.5 into e to the power minus tt. So can I calculate Ct tending to infinity? So what will be the value t tending to infinity? Tell me. So if we say at t tending to infinity, it will be equals to 0. So the value of this one will be 1.5. Now, what will be the value of your offset? Offset is equals to what? M minus this one, that is 1.5. So 3 minus 1.5, that is equals to 1.5. So this will be your offset. Is it clear? Anyone has any doubt? Darshana, is it clear? Okay. So till now we have seen offset for only set point change. When, since if it is a your control loop transfer function, and here this is your GC, this is controller, this is your G final control element, and here there is a load, right? U, and here if this is your process, fine. So this one is your output, this one is your input XS, and here if I'll get in YS, right? And uh, again, this is a negative feedback control system I am assuming right now. And here there will be a measuring instrument, and output is getting feedback over it. So since this is called your set point, and this point is called as your load, fine. So since I have told you that if set point change is happening, if this is happening, then it is called as the servo problem. And if load is changing, then it is called as the regulatory problem. So till now, I have seen that set point change is happening and load is equals to 0. That is called as the servo problem. For that offset we have seen offset is equals to m, that is magnitude of a step input minus y when t tending to infinity. And for this is only valid for step change input, and this is your ultimate value of your closed loop response. This was the formula of your offset for servo problem. But when we talk about regulatory problem, so in regulatory problem, what do we do generally? In regulatory problem, what happens? Your set point change will be equals to 0. So if I will define formula of offset, so what happens? Offset is equals to m minus, that is m is change in step input minus y at t tending to infinity, right? But here m will be 0. So what will happen? Your offset will be equals to 0 minus y t tending to infinity, right? 0 minus y t tending to infinity. I hope this thing is clear to all of you. Okay? Anyone has any doubt? So let's say if I am trying to control a process like that, yeah. So this one is a process having kc is equals to 1. I'm giving you the simplest example so that you can solve it. And this is 1 upon s plus 1. This one is your c, and this one is your load, right? Again, here is an input, right? So x, xs is equals to 0, right? So calculate offset if u is getting changed with a step input of 5 magnitude, right? So how can I solve this offset for this particular process? Calculate offset for this particular process. First, just try the way I told you. I mean, in case of regulatory problem, the set point change will be 0. So according to that, you have to understand this thing.